everyone. Today I'm going to be going over question 16 from chapter 5 of the textbook. It's going to be on Huffman encoding, and we're going to prove some guarantees on it. So part A, if some character occurs with frequency more than 2/5, then there is a guarantee to be a code word of length 1. So you can pause the video and take some time to try it yourself, but I'll get into it. So the way you generally approach these questions is by constructing a proof by contradiction. So we'll sort of assume that there's both a character with frequency 2/5, greater than 2/5, and there's a code word of length 1. And then we'll prove that sort of this cannot exist, thereby proving that if some code word occurs with frequency more than 2/5, then it's guaranteed to have a code word of length 1. So generally, when you don't have a code word of length 1, you end up having this sort of tree. You end up having this tree where symbols A and B are combined, symbols C and D are combined, and then they're combined all together. And this can be sort of either C and D can be combined first, which is case 1, or A and B can be combined first, which is case 2. And so here, both of them will have some sort of both all symbols A, B, C, and D will have a length of at least 2. And so, like you can already see, we'll construct this proof by cases. I'll start with case 1, which case 2 actually, which will be a bit simpler, since without loss of generality, we can assume that the frequency of A is greater than 2/5, and since FA is less than FC and FA is less than FD, since it was combined first with B in this algorithm, which means that symbols A and B had the smallest frequency, we can see that symbol C had a frequency of greater than 2/5, and symbol D had a frequency of greater than 2/5, which means that the sum of the frequencies was greater than 1, which cannot exist. Contradiction. Now for case 2, this will be a bit harder. So once again, we know that FA is greater than 2/5. However, now sort of FC and D are combined first, which means that FC is less than FA and FD is less than FA. Less than FA, and also FB. However, once C and D are combined, then A and B become the smallest tokens, which means that FC plus FD is actually greater than FA and FB. And we can combine this with another equation, that FA plus FB plus FC plus FD has to be equal to 1. Now, it might be a bit hard to see, but in these equations, there's actually a contradiction. So the way we can sort of sniff it out is we can see that FC plus FD is greater than FA, which is greater than 2/5. And FB is greater than FD, and FB is greater than FC. Well, actually, if we just take this and plug it into this equation, we'll see that FB has to be less than 1/5, since FA, FC, and FC plus FD are both greater than 2/5. FB has to be less than 1/5. However, since FB is, now we can bring in these two and say that FB has to be greater than FD and FB has to be greater than FC, which means that 2FB has to be greater than FD plus FC. However, it also has to be less than 2/5. 2 times 1/5 from this equation, we can see that we actually have a contradiction between this statement and this statement. So to recap, what we did is we sort of, from the fact that there's no code word of length 1, we created this sort of generic Huffman tree and analyzed it by cases in sort of which order the symbols are combined, and then proved that for any order of the symbols can be combined, FA, if FA is greater than 2/5, then sort of this tree cannot exist, which implies that there is guaranteed to be a code word of length 1. Now for part B, we're also going to prove it by contradiction, and we'll actually have 3 cases. So case 1, 2, and 3, where you can have a code word of length 1, and some of these will be trivial. So if you just have symbol A and its frequency is less than 1/3, well, you can see that it sort of cannot exist since the frequencies don't add up to 1. Similarly with this case, if all the symbols have a frequency of less than 1/3, it just cannot add up to 1. And in this case, it might actually be a bit harder, since B and C don't. B and C could be sort of the sum. It could be the sort of products of combining other symbols. So you can just say that FA is less than 1/3. However, since B and C are combined before before A is brought in, B and C both have to be smaller than A. And so that the sum is also smaller than 1, which is a contradiction. So this is a sort of maybe easier than part A, and just has more cases where you have to really make sure that you cover all the cases where there's a code word of length 1, and then for all of them prove that that tree cannot exist. And so that's pretty much the general approach to Huffman. You look at the algorithm, you sort of see, you can sort of by cases assume what it combines. From there, you can derive the equations, sort of inequalities to show which is less than what. And from that, you'll get that the sort of something in the end breaks down, and you'll be able to prove your original statement.